So how do we get charged objects? We have to transfer the charge from one object to the other one. So everything starts out neutral, same number of electrons as protons. And when we rub the two objects together, one of the materials has a stronger affinity for their electrons than the other material, and it will grab on to some of the electrons from the other material. The one that picks up electrons becomes negatively charged. The one that loses its electrons now has more positives than negatives, so it is positively charged. We don't transfer positives, right? That's in the nucleus. We can't get those to move. But this cloud of electrons, those are the things that we can get to move when we rub things together. So let's take a look at that. Let's see, rubber and hair. My hair, when I rub it with the balloon, becomes positively charged. The balloon becomes negatively charged. And then they will, it'll stick to something, right? Well, first of all, hold on. I rub it against my hair. One of them becomes positive, one becomes negative, right? My hair is positive, balloon's negative. So what happens when I do that? So what do we know now about opposite charges? They attract each other, okay? And let's see what happens with like charges. Can you see the balloons hanging over here? You thought it was my birthday, didn't you? This is a demonstration. So we'll rub the balloons. And what's going to happen to the balloons? They're the same charge now. Is that correct? Maybe it's not so obvious. Is it obvious? They're repelling each other. Oops. And they're attracted to me because I rubbed them, right? Let me try one more time. We'll come back to that. My hair's all messed up now. Okay, so we rub things together. They become electrically charged. Let me do this one for you then. PVC, piece of PVC pipe, and wool. So the wool becomes positive, the PVC becomes negative. I have a little bit of PVC shopping bag, Safeway shopping bag or something. Now they're charged the same charge. Oops. So I should be able to, I'm a little out of practice, I guess, get this to, you can see that there's a interaction, right? Maybe it's more obvious with the balloon. That's a little easier, isn't it? So those are both charged with the same type of charge. Did you notice? Because both of these materials, they're both sort of plastic, rubber materials. If you look in the book, they've got a little table. They both become negatively charged when rubbed with wool or hair. And so I've got two objects that are the same charge. And what are they doing? Repelling each other, right? But if I rub this thing against my hair, I'm the opposite charge, so it sticks to me. Okay? So there's another interesting effect called induction. Where we get the object to act like it's charged even though it's neutral, because we can get the charges to separate. So let's take a look at what happens. Let's say I have a conductive sphere hanging here. And I bring up a charged object. What charge should we make it? Positive? So what's the definition of a conductor? Electrons are free to move, right? So what's going to happen? What's going to happen to the electrons in our conductor? They're going to be attracted, right? Opposites attract. They're going to be attracted to the positive charge I have over here. So they move to the left side. The positives don't move, but what happens, each electron was associated with a particular atom. Now some have moved, so what's left behind, sort of unshielded by those electrons that have now moved? Positives. So I'm going to draw them on the other side because that's basically where they would be. The electrons are going to come from as far away. So we've got this situation. That sphere is still neutral. But the charges have separated a little bit. And an important thing with electrical forces, actually just like with gravity, the closer the objects are, the bigger the force. Closeness counts. So even though this object's neutral, the negatives are closer than the positives. So we're going to see, well, let's see what happens. We're going to see a net force. Here's my conductive ball right here. And I'm going to touch it, make sure it's not charged. I'm grounding it. Okay, now I will charge up my PVC. And let's see if we can get a... is it leaning? Oh! I think it got attracted. Did you see that? Leaning over that way. Is that an attractive force? I think so. You need to see it on this side. Oops. Okay. Attractive force. Now, an interesting thing happens. What happens when they touch? Okay, closeness counts. So we get this attractive force, and they touch. And what do you think is going to happen now? When they touch, charges can move between them. This one has some excess negatives. That's what we said, right? The PVC pipe has excess negatives. They're all sort of repelling each other, but they can't move around because this is not a conductor. They're stuck where they are, but there's excess negatives there. And when we bring it up next to the conductive ball, they attract at first because we have that charge separation. But once they touch, some of the electrons might transfer over. And then what happens? Then we have two objects that are the same charge. Because they don't all go over there, right? A few transfer over. Okay, so let's see what happens. Okay, so they touched. And now, can you see that? Now they are repelling each other. Okay? So they touch, and some of these excess, I guess I've drawn it differently here. Some of these electrons move over, and then what am I left with? I still have a positively charged rod with a few extra electrons, and I now have a positively charged conductive ball, and they like charges repel. So you're probably wondering, well, which is it? When is one effect more important than the other effect? Usually, a net charge dominates. So in this case, the sphere has a net charge on it, right? The objects touched, electrons transferred, we have a net charge, and now we have two objects with a net charge. If that's the case, that effect usually dominates, unless the object is very long and the charges can move far away. Usually, the net charge dominates. When the object's neutral, then these more subtle effects come into play, like charge separation over the distance of the object. Okay? So we call this an induced charge separation, or some people say induced charge. I like to say induced charge separation. So the object's not charged, but it acts like it's charged because the charges have separated. Okay, let's look at a couple of other examples. Let's see. So this was a conductor, and maybe it's easy to see why we would get this in a conductor, right? Charges are free to move. We put a charged object up next to that conductor, and it's going to exert forces on the charges in the conductor, and they're free to move, so they're going to move. You exert a force on something, and it can move, it's going to move. But what happens with an insulator? What happens if we hold our charged rod, doesn't matter, negative, positive, over a piece of paper? Are they going to be affected at all? Should we see what happens? I have some paper here. Okay, you watching the little piece of paper? What happened? They were attracted, weren't they? Are they stuck to my rod, though? No. What happened when as soon as they touched my rod? They were repelled. So it's similar to this, right? They were initially attracted because these are neutral, and we got some kind of a charge separation. I'll talk about that in a second. And so we got an attractive force because closeness counts. Then as soon as they touched, some charges transferred, then they were like charges repel. So let's see, how could we get a charge induced? How could we get this separation to take place on an insulator? Right? That's the big question. So let's take a look at this piece of paper. I'll magnify it a little bit here. There. So that paper is made up of molecules. And normally, the electron cloud is pretty well centered around the nucleus, right, shielding the nucleus. But if you bring up a charged object, the electrons, they can't leave. This is an insulator. They're tied to that atom. They cannot leave and move around through the material. But what can they do? They can shift a little bit. They're still stuck to that atom, but they can shift a little bit in one direction or the other. If they're attracted to a positive force, they can shift toward it a little bit. If it's a negative force, they're repelled, they can shift in the opposite direction a little bit. So what we end up with is the molecules, instead of being perfectly symmetrical, the molecules take on sort of an elongated shape if you were to look at them electrically, right? Where one side, we call it a polar. It's now the molecules become polar. One side is negatively charged and the other side is positively charged. And this is because we are bringing up a charged object next to it.